Again, next week is our last week. Next week we have our final exam. Beginning Thursday, we will begin our review. We're going to spend 3 days in review, Thursday, Monday, and Tuesday. Thursday, our review will be completing this quiz. So I'm asking you to go ahead, because we won't have time in class Thursday to go through 120 items. But what I will do is I will make confirm for you the ones that you have. If you couldn't find it, couldn't find the number, couldn't find the equation, couldn't find it, then I will make sure you have it Thursday, because I want you to spend the weekend reviewing these. I may even give you like a practice exam just to see how well you're able to do these. Okay, let's move to our lecture for today. Okay, so let's move all the way down to where we are for today's lecture. And we're going to start with number 105. So 105 is convection. So that is, these are terms from chapter 13. And I sent you some lecture notes from chapter 13. So our first term is convection. So what is convection? Convection is the process in which heat is carried from place to place by the bulk movement of a fluid. And remember, we said that for physics, when we use the term fluid, we are referring to a liquid or a gas. A gas or a liquid is what we consider a fluid. So what is convection? The process in which heat is transferred from place to place by the bulk movement of a fluid. So for example, when you put an object on, when you want to cook something on the stove, and you want say you want the egg to cook inside the hot water. It is the heating up of the water that actually cooks the egg. And the water, of course, is a fluid. So that's an understanding of convection. Now, or you can think about your the heater in the furnace in a room. The furnace gets hot, and the air moves that hot heat throughout the room. The air in the room, the air being the fluid that moves the heat throughout the room. So that is the understanding of convection. Okay. Our next term is conduction. So what is conduction? Conduction is the process whereby heat is transferred directly through a material, with any bulk motion of the material playing no role in the transfer. So, whereas convection involves a liquid or a gas, like in the case of fluids, by conduction, we are talking about a solid material, because we're saying it's directly transferred through a material. Now, of course, we know we can transfer it through, what I'm saying is it can be a solid, a liquid, or a gas, but in the case of convection, of course, we can't conduct through a solid the way we can through a liquid or a gas. So conduction then is the heat that's transferred directly through a material, and this material can be a liquid, a solid, or a gas. Now, think about when you put a metal, like a cast iron skillet, on the stove. You put that cast iron skillet on the stove. After a while, that entire cast iron is hot. Even the handle is hot because the heat has been transferred through the entire bulk material. So that's what conduction is. Or think about you put a poker in the fireplace. You're gonna try to stir the fire, and you leave that poker there. You forget about it. You come back and you grab it, and you will burn your hand because all that heat now has been conducted through that metal, and the very tip of it is now hot as well. That's conduction. Our next term is, oh no, so we have an equation. Heat conduction through a material. So let's write that equation down. So I'm at 108. So we have an equation. I'm going to go to the whiteboard so I can have more room to explain to you the terms for heat conduction through a material. So I'm going to go to the whiteboard. Okay, you see the whiteboard? Now, what is the equation for conduction of heat through a material? So we know we use the symbol uppercase Q to mean heat transfer, or heat, in this case, the heat that's transferred through the process of conduction. So it's equal to kappa, that is the Greek letter kappa, okay, times A. I'll explain everything to you in just a minute. Change in temperature, delta T, all of that times time divided by the length of the material. So what is the kappa? Kappa is the thermal conductivity of the material. So I know that doesn't look like the, let's see, lowercase k. Let me see if he calls that kappa. Hold on, let me make sure. I think he calls that kappa, but I didn't hear his lecture. So let me look at my Greek letter real quick to make sure I'm not calling that. Okay. No, let's just call it lowercase k because it doesn't look almost, it looks like a lowercase k rather than a kappa. So just call that lowercase k. Okay, lowercase k then is the thermal conductivity of the material. If you have your textbook on page 365, table 13.1, thermal conductivities of selected materials. Okay, so let me give you a value. For example, I'll give you the conductivity for water. For water, H2O, the thermal conductivity is 0.60. Now look at these units. The units are joule per second times meters times degree Celsius. That is the thermal conductivity for water. If you notice in the, we have a problem coming up we're going to solve in just a minute, but that is the thermal conductivity. Now, the area, of course, in this section is the cross-sectional area. Now, the cross-sectional area will be determined by the shape. If it's going through something that's got a circle at the end like this, the cross-sectional area would be the area of a circle. However, if it's going to be, more rectangular shape like this, then a cross-sectional area would be like a rectangle. So make sure in the problem you understand what is a cross-sectional area. Then we have the change in temperature. This we've already had. That's always what? Temperature final minus temperature initial. Then we have a time. The time is in seconds. And then we have the length. So this is what is meant by conduction um, of heat through a material. Okay, that's that equation. Any questions? So let's go through the example that the author gives for conduction. So I'm looking at the example he gives on page 366. Okay, so as always, we want to identify what is given in the problem on our chart. So the question says, when excessive heat is produced within the body, it must be transferred to the skin and dispersed if the temperature at the body interior is to be maintained at normal body temperature. Now we know the temperature needs to be in degrees Celsius. So last time we learned that the normal body temperature for the human body is 37 degrees Celsius. Remember, we did the conversion from 98.6 to degrees Celsius. So in this chapter, whenever they talk about the human body, this is the temperature for normal body temperature. One possible mechanism for transfer is conduction through body fat. Suppose that heat travels through, so it's giving you how much the length that the heat is transferring through. It says it's 0.030 meters of fat in reaching the skin, which has a total surface area. So the surface area for the skin is 1.7 meter square. And a temperature of, so the temperature initial is, so this would be temperature final, because this is the body temperature. Temperature initial is 34 degrees Celsius. The question is, find the amount of heat that reaches the body. Find the amount of heat, that's Q, that reaches the body of the skin in half an hour. So my time is 30 minutes. Okay, find the amount of heat that reaches the skin in half an hour. So what equation are we going to use? We're going to use the equation for conduction of heat through a material. So that equation again is Q equals lowercase k, cross-sectional area, change in temperature, times time, divided by the length. Now, that means the first thing I need to know is, what is this K? And in my chart, I can find K, which is the thermal conductivity of body fat. So let's see if they give us that, okay? So it says for body fat, right here, the K for body fat, they say is, in this chart, 0.2 times, oh no, it doesn't have any exponents, hold on. Okay, 0.2, what are my units? Joule per second meter degree Celsius. That's the value of K for body fat. So now I can plug everything in. Okay, so what is K? 0.2 joules per second meter degree Celsius. Okay, times the area. The area they said is 1.7 meters square, the area. Okay, times change in temperature, 37 degrees minus 34 degrees. So my delta T, oh, I'm sorry. My delta T is 3 degrees Celsius. My time, okay, I'm applying all this. My time is 30 minutes, but of course needs to be in seconds. So I have 30 times 60 seconds per minute. So therefore I have times 18, right? 1800 seconds, okay? Divide everything by the length, and the length it says was 0.03 meters. Now, we know that Q is measured in joules. So the first thing we need to make sure before we do any math is that the units all cancel except for the unit of heat, which is joules. And sure enough, meter times meter would be meter square. So that's going to cancel out. And we have seconds and seconds. That's going to cancel out. And degrees Celsius and degrees Celsius is going to cancel out. So before we even do the math, we have a pretty good assurance that the problem is going to be correct because we have the correct units. So when we solve all that, the author says that we should get 6.1 times 10 to the 4th joules. So I didn't solve it out, but I think that should be correct. You can put in your calculator and see if that's what you get. Okay, so that equation then is just and you have a problem like that in your homework, but I want to show you something in the homework when we get to it, because what you'll notice is, and I hope you'll notice this, is that when we have joule per second over here, well, I'll show it to you in the problem. I'll show it to you later. Okay, so any questions on this problem? Just basically want to help you understand this equation, which is the conduction of heat through a material. Okay, very good, Kayla. Okay, very good. All right, now I asked you to have a calculator because we are going to be doing some problems in the assignment together here in very shortly. So make sure you have your calculator, pencil, and paper ready. Okay, let's move on to with our lecture. Okay, so our next term is radiation. So in the textbook, I'll give you the definition for radiation. It says, radiation is the process in which energy is transferred by means of electromagnetic waves. Now, when we speak of electromagnetic waves, actually the chapter after the last chapter we're going to cover is wave motion. But I'll tell you quickly that the electromagnetic wave is the movement of EM waves, which all move at the speed of light. So when we speak of EM waves, we're talking about light waves, visible light waves, infrared, microwaves, all of the waves that are in the electromagnetic spectrum. So let me read this part to you. Energy from the sun is brought to the earth by large amounts of visible light waves, as well as by substantial amounts of infrared and ultraviolet waves. These waves are known as electromagnetic waves, a class that also includes the microwaves used for cooking and the radio waves used for AM and FM broadcasts. And we'll go through more of that in the next chapter. But the important thing is that it is transferred by means of electromagnetic waves. And these waves, class, can move through materials, and they can also move through a vacuum. In other words, the electromagnetic radiation can move through nothing. It can be an absolute vacuum. And of course, those waves will still radiate. So we have another equation called the Stefan-Boltzmann law of radiation. So let me go to the whiteboard and show you that one. Okay. So what we have found, what astronomers and all those people who study radiation and heat energy and heat energy transfer know that the radiation, the heat energy that's through heat transfer by radiation is equal to sigma, that's lowercase sigma, the temperature to the 4th power times the area times the time. That's the equation. Now, this equation is only for what we call a perfect emitter. And it only holds true for a perfect emitter. So since most things are not perfect emitters, because they're not perfect emitters, let me show you what we have to put here. Let me just show you real quickly. We have to include in this equation what we call the emissivity constant, okay? E. E stands for the emissivity constant. So now we have the Stefan-Boltzmann law of radiation, where the E stands for the emissivity constant, okay? And if you have your textbook, again, there is a chart that gives you some of the emissivity values. I mean, the emissivity ratio is actually a ratio of what? The energy the object actually radiates divided by the amount of energy the object would radiate if it were a perfect emitter. So it's some number between 0 and 1, point something and 1. So and for a perfect emitter, it would be just what? It would be just 1. So that is the emissivity constant. It's a ratio. You have for example, I think for the for visible light, it's about 0.80. The emissivity value for light, it's about 0.80. I think it is, or some range close to that. Now, what is this sigma? Sigma is a lowercase Greek letter. Also, last time I sent you a picture. I sent you a picture with the Greek letters. Because we're using these so much now, I wanted to make sure that you could name them. So I sent you a chart, and I can't always draw it the best, but that is lowercase sigma. Okay. The chart that I gave you had, I think I was trying to point out rho, because remember we use so far we've used theta a lot. We've used pi, of course, a lot. We've used pi a lot. We used alpha in the last chapter. We used alpha. We used omega. Now we're using sigma. Let's see, what else have we used? Oh, later on in the next chapter, we're going to use lambda. So I sent you that because what I was saying to one student, because we only have so many variables, so many letters that we can use for all of these many equations, we also incorporate Greek letters. So in this chapter, we see we have a couple of more. So we have sigma. Now, what is sigma? Well, sigma is the Stephan-Boltzmann constant. It's a constant because actually the Q is proportional to the temperature, the area, and the time. It's proportional to. So this is a constant that's needed to solve the equation, the constant proportionality, sigma. So that value is 5.67 times 10 to the minus 8, another very, very small number, joule per. Now we have second, and we have meter squared. Remember, the other one was meter, and this is meter squared. And now my temperature is not in Celsius. For this equation to work, we have to put the temperature in degree Kelvin to the 4th power. So that is this Stefan, some folks say Stefan, some folks say Stefan Boltzmann constant, or Stephen Boltzmann constant. Okay, so now we have the law and we have the constant. Then the temperature in this equation is raised to the 4th power. We have the area, and we have, now this area class, because this is a black body or a body that's radiating, this area is the surface area, So we've already learned that for a sphere, the equation for surface area for a sphere is 4 pi r squared, surface area. So, and then we have the time. So that is the Stefan-Boltzmann constant. Let's go back to our chart, to our equation quiz. Okay, so I've given you the Stefan-Boltzmann law of radiation. I've given you the value for the Stefan-Boltzmann constant. And now notice here that this is kind of small, so you may not be able to put the unit there because you notice that this unit now, for this constant is not simple. Now we know heat conduction, that unit is always going to be joules. So of course a joule will go here, a joule will go here. But for here, for this constant, of course, it may not all fit on this little small space. And then we said the emissivity is a ratio of the energy the object actually radiates compared to the energy it would radiate if it had been a what? A perfect emitter. That's a ratio. It's a number with no units. Okay, so with that being said, that's all I have for this chapter. Now I'm going to save these next 2 chapters here for Wednesday. But if you want to go ahead and go through your textbook and finish putting all these down, this is right out of your textbook. Well, you know what? I'm going to go ahead and put these down so that we will have these. Let me just go ahead and put these down. Let me see. Yes. And then when we come back next time, we can just solve these equations. Let me see. Well, my pen's not working on this page. Here it is. Okay. So we say the ideal gas law, we can write it 2 ways. PV equals nRT, or P1V1 equals P2V2. I'll go over this for you again. Just write it down for right now. Bohr's law, over T1 over T2. So in Bohr's law, we keep, let me just say this for tomorrow. I'll say this for Wednesday. I only have to do a few. So I should be able to do these, a few examples, and we still can start on our review on Thursday. But if I were you, I would go through my textbook and finish filling these out. I would finish filling these out. Wave speed is frequency times wavelength. So lambda is going to stand for wavelength. But you can finish filling that out later. I want to solve a few problems now and go through some of the quiz that I gave you. Okay. So in your notes, assignment 1, I gave you these these questions. So number 1 says, complete the following statement. The transfer of heat by convection. I'm just seeing if you understand what we just said about convection. So remember, convection is what? If you didn't write it down, can you visualize it there being a fluid being a gas or a liquid, and what's actually happening in the convection process? Okay. The process in which heat is carried from place to place by the bulk movement of a fluid. So which one of these will be the transfer of heat by convection? Will it occur only in metals, only in a vacuum, only in non-metallic solids, with or without the presence of matter, only in the presence of a liquid or a gas? So what's your thoughts for number 1? I'll go to chat and put in your answer for number 1. The transfer of heat by convection will occur A through E. What do you think? I'll give you the definition again. Convection is the process in which heat is carried from place to place by the bulk movement of a fluid. A fluid meaning a liquid or a gas. So is it A, B, C, D, or E? Give me a letter, please, for your answer. Let's give me a letter. Rest of you, give me a letter, please. This is how we're going to, okay, very good, Nigel. Okay. Okay, so listen again to the definition for convection. Convection is the process in which heat is carried from place to place by the bulk movement of a fluid. And by fluid, we mean a liquid or a gas. So for number 1, the answer would have to be E, only in the presence of a liquid or a gas, because that is the heat is being carried through the movement of these fluids, liquids or gases. Okay, number 2. Which one of the following statements best explains why convection does not occur in solids? Okay, think about a solid. Okay, so what are my choices? Molecules in a solid are more closely spaced than in a gas. The molecules in a solid are not free to move throughout the volume of the solid. Molecules in a solid vibrate at a lower frequency than those in a liquid. Solids are more compressible than liquids. Solids are less compressible than gases. Now the question is, which one of the following statements best explains why convection does not occur in solids? And again, what does convection mean? The process in which heat is carried from place to place by the bulk movement of what? Of a fluid, a gas or liquid. So we know that what? Very good. Okay, Nigel. The molecules in a solid are not free to move throughout the volume of a solid. In a solid, the molecules are what? They're fixed in place. They have some vibrations, but for the most part, what the bulk of the body is a solid, not like a liquid or a gas. So we're going to say B for that one. Okay, number 3. Which one of the following is not an example of convection? Okay, look at that one. Okay, so number 1, we said the answer was E. And number 2, we said the answer was B.
Are we supposed to be saying something?
Yeah, you're supposed to be putting your answers. Do y'all not see what I'm working on? Y'all don't see the answers?
I still see the equation quiz.
Oh, I am so sorry. Let me, okay, thank you. Let me just see. Okay, how about now? Can you see it now?
Yeah, we can see
Okay.
that. Yeah, I
All
was
right.
having difficulty relating which letter to what answers you were giving, so that was wrong.
Okay, but also I had sent this to you in your email. You may not have pulled it up yet, but I sent this to you as well. Okay, thank you for bringing it to my attention. Which one of the following is not an example of convection? Look through it and tell me which one of the following is not an example of convection. Convection is the what? The bulk movement of a fluid from carrying the heat from place to place through the bulk movement of a fluid. Okay, so let's go through. Give me your answer for number 3. I'm waiting for someone to give me some answers. A, B, C, D, or E. Not an example of convection. Remember, convection means what? The bulk movement of the fluid. Okay, so on this one, class, think about what's happening. Smoke rises above a fire. That means that what? The air, we can see smoke. Smoke is a gas. An eagle soars on the updraft of wind. The wind is gas, is a fluid, that's air. A person gets a suntan on a beach. What's happening there? That's what? That's radiation. That's the heat from the sun landing on what? On the person's skin. So that would be what? That would be an example of radiation. Spaghetti is cooked in water, of course, that's what? That's convection. Electric heater warms a room, that's convection. So the answer we should choose, class, should be C. Which one of the following is not an example of convection? That would be C. Okay, so answer the rest of these. You can send this to me by 1 tomorrow so I can give you the answers. Well, no, it'll be Wednesday because I won't be able to check it tomorrow, but go ahead and work on it. And so you have all these that you're going to work on. Now, let's do a problem together. I'll set one up. So I wanted to show you something on this problem. And then we can, okay, so now you'll notice that most of these questions this time, class, are just helping you to understand the concept of the transfer of heat through what process? Convection, conduction, or what? Radiation. So read through these and answer these questions. Now we have a problem. Our problem is number 10. So number 10 says, at what rate is heat lost? Okay, so at what rate is heat lost? So remember we said that heat loss Heat is in joules. Let me get my pen, hold on. Heat is in joules, and the rate of anything is what? That object or that quantity per unit time. So a joule per unit time, of course, that is a what? That's a watt. Joule per second. A joule per second. I said per time. Let me put that. Hold on. Let me take that out. Well, I'm trying to say joule per second. That's a watt. Okay. So that's why we have these units here in watts. Now, what is our equation? Let me go to the whiteboard so I can have a good use of my pen. I don't have good use of my pen here anymore. So let me do a new share, go to my whiteboard, and solve this problem. Okay. So which equation am I going to use for the conduction of heat? And that equation is what? Who knows the equation? Can someone come off the well, I'll just go ahead and write it down. Okay, Q is the what? Constant times the cross-sectional area, change in temperature times time divided by what? The length. Okay, so if we're going to find something in watts, we can tell here this implies that I'm looking for heat energy per unit time. Heat, so I'm going to divide through by time. So that's going to be K A delta T divided by L. Okay, so the question says what? Let me go back to the question. This is number 10. At what rate is heat lost through A? So we have the dimensions, the length, it seems to be 1.5 meters. The width is 3 meters, rectangular glass, window pane, and they gave us the thickness. So the thickness is the length, 0.4 centimeters. When the inside temperature is, so the temperature final, the inside temperature raises to 22 degrees Celsius, and the outside temperature is 6 degrees Celsius, and it gave us the value for K, which is the thermal conductivity for glass, and it says that value is 0.75 watts per meter degrees Celsius. Now you notice earlier when I gave you a value for the thermal conductivity, I said joule per second, because a joule per second is a watt. And that's why we can give it in that form also. So when you solve the problem, then you're gonna plug in these values and let me see what you get. So you're given what? You are given the value for the thermal conductivity, you know, the area, because you know the length and the width. You can find delta T here, and you know the thickness, which is the length. Okay, so let me see you solve that problem and let me see what you get. We're doing number 10, and look at your handout. We'll solve it first and see what you get, and then we'll go back to the handout and we'll see what the answer is. So all you're doing is putting in these values. Okay, you're putting in 0.75 watts per meter degree Celsius. That's the thermal conductivity K. You put in a cross-sectional area, and that is 1.5 times 3. And of course, this is meter times meter, so it's meter square. Okay. You're putting in delta T. You got 22 minus 6, and of course, that's 16 degrees Celsius. And you're putting in the length. But look, the reason why you know the length has to be in meters and not centimeters is because the meter square needs to cancel a meter here and this unit in meters. So of course you're going to put in 0.004 meters. And why is that? Because you can't put in centimeters. Because see, meter times meter is meter square, and that will cancel out the meter square. And then we have degrees Celsius, cancels out degrees Celsius. And my answer will be in watts, which of course is joule per second, which is the rate of energy heat loss. Okay, so what do you get? Use your calculators, please. Just give me the number, then we'll go and see what that letter is. I'm waiting for. Okay, so you got 0.75 times 1.3 times 3 times 16 divide 0.004. Okay, I'm seeing some correct answers and I'm seeing some incorrect answers. Now class, all you're doing is putting these numbers in your calculator. Try it again, everyone. Well, I think that, okay, Lanisha, that looks good. Lex, that looks good. Okay. Nigel, that looks good. The rest of you, put it in your calculator again. See what the problem is. Put in your calculator slowly, so, and then look at your numbers again. Make sure you're not putting it in incorrectly. Okay, Kaylin, that looks better. Kesson, that looks better. Okay, very good. All right, so let me go back to so the answer then should be E. You should all get that answer, E. Okay, very good. Now, these other questions, as you can see, are just questions for you to understand conduction, convection, and radiation, those terms. But later on, we have some problems to solve. So we have problems to solve 15, 16, 17, 18, 19, and 20. Then again is one of your thought questions. So let's choose one of these and let's work it. Let's look at number 19. So the equation we just used earlier, that's the equation for the thermal conductivity through a material. Now we're going to do one where the object is radiated from a perfect or some kind of emitter. So we have a different equation for that. So let's go to our whiteboard and solve number 19. Okay, so this is the equation for the heat that's transferred through a material. Now we're going to use the Stefan Boltzmann equation law to solve the next problem. Okay. So what is our Stefan Boltzmann law? We say that energy is equal to, okay, so write it again. Q is equal to the emissivity times the Stefan Boltzmann constant, temperature to the fourth power, the area, and the temperature. Now, it says that the power irradiated by a distant star. So they gave us the power. And that is 6.2 times 10 to the 27 watts. So already we see that we have what? Q over T, because Q over T is watts. So this T is over here now. And that's what's given. Q over T. That's power. That's what's given. The rays of the star, which may be considered a perfect radiator. A perfect radiator means that my emissivity is going to be 1. So I don't have to use that. And that value for the radius, they say, is 1.06 times 10 to the 10th meters. And it says, determine the surface temperature of the star. Determine the temperature. So we know then that Q over T, which is our power, is going to be epsilon temperature to the fourth power times area. So my equation then is my temperature to the fourth power is equal to Q over T, which is power, divided by sigma, divided by the area. And this, of course, is the surface area of a what? Of a sphere, because we know that a star is a sphere. So then we're going to have, pencil, okay, power divided by sigma, and my area now is going to be what? 4 pi r squared. That's the surface area of a sphere. Then to find the temperature, whatever this is, I'm going to take it to the 1/4 power. That means the fourth root. The fourth root means the 1/4 power. Okay, so now let's plug in what we have. So my temperature to the fourth power, let's solve it first. I want to show you a little trick right here. Okay, so what is my sigma? Remember that number? We said it's 5.67 times 10 to the minus 8. And remember, a joule per second is just a watt, right? So if it's a joule per second, we just call that a watt divided by, since we have watts here, we're going to say a joule per second is a watt. And then we said it had to be what? Meter square. And then Kelvin to the what? To the fourth power. That's that number. So let's plug in our values. Power, 6.2 times 10 to the 27 watts, divided by sigma, 5.67 times 10 to the minus 8 watts per, remember, when it's in the denominator of the denominator, it moves where? To the numerator. Okay, meter square, Kelvin to the fourth power, temperature in Kelvin to the fourth power. Now, if we were looking for this temperature in Celsius, when we finish with this, we would convert it to Celsius, but we have to plug it in when we find it's going to be in Kelvin temperature. Okay, And the area, the cross-sectional area is 4 pi r, and r is 1.06 times 10, hold on, times 10 to the 10th, and that's to be squared, and meters to be squared. So the first thing you want to do, class, is make sure that everything cancels out but the temperature in Kelvin. So sure enough, we have watts to cancel watts, and we have meter square to cancel meter square. So it's going to come out in Kelvin to the 4th power, and that's what we want. Okay, so let's do the work. In your calculators, you have 6.2 divide 5.67, divide 4, divide pi, divide 1.06 squared. So let's do that part first, very carefully. Do that math very carefully and see what you get. I want to see that number first. Before we go any further, I want to see that number. Then once you get that number, you're going to have 10 to the something, and you're going to have k to the 4th power. So first, I want to see this number. What is everybody getting for that number? In your calculator, just divide 6.2 by this number, by 4, by pi, and by 1.06 squared, and see what you get. Take your time. Don't be afraid to show me your answer, because that's how I can tell you where you have an error. If I don't see any answers, then I won't know if you're making a mistake or not. Now, we're not doing the exponents yet. We're going to do those separately. Okay, no one can give me that number? Okay, class, do you have your calculators in front of you? I don't see the correct answer from anyone yet. We're all using these exact numbers. We're not changing them. We're not rounding them. We're putting in these exact numbers. Okay, let's just do it together. We have 6.2 divide 5.67. When we do that, we get 1.09. Then we divide that by 4, and we get 2.273. Then we divide that by pi, and we get another number. Then we divide that by 1.06 squared. And finally, we all should get 0.07744. That's the number that we all should get. Now, if we're using our calculators, it shouldn't take several minutes just to put those numbers in the calculator. Now, once we do that, we've taken care of the numbers. We've done that, we've done that, we've done that, we've done that. We haven't done this part. Okay. Now we have 10 to the 27th in the numerator. The denominator, we have 10 to the 10th to be squared. That's 10 to the 20th. So in the denominator, we have 10 to the 20 minus 8. So in the denominator, we're going to have what? 10 to the 20 minus 8, we got what? 12. On top, we have 27. So taking care of everything now. So now, what I want to show you is this. The best way to solve this kind of problem, class, is to think about how easy it is to raise even numbers to a power as opposed to odd numbers. In other words, when I say 0.07744 times 10, 27 minus 12 is 15. Okay, k to the fourth. So now I want to take the fourth root of that. So watch this. This is why I want to show you this problem. If I make this problem to the 16th, then of course 1/4 of 16 will be 4. 1/4 of k to the fourth will be 1, k to the first. And then I just take the fourth root of this problem. That's the beauty of understanding how to use these exponents. So I have 0.00774 times 10 to the 16th k to the fourth power. Now, when I get ready to find t, because I want to find t here, I take the fourth root of this number. So in my calculator, I take this number to the 1/4 power. Okay, I take this number to the 1/4 power, that's just 4. I take this to the 1/4 power, and of course, that's just 1. So now, this number to the 1/4 power, what do you get? Put in your calculators 0.00774 and raise it to the 1/4 power. Please do that. Okay, very good. Now, you're going to get 0.2966, okay, times 10 to the what? To the fourth. 10 to the fourth means what? Move it over 1, 2, 3, 4 times, and my unit is K. So I get 2966 Kelvin. That's the answer I get. Okay, let's go see this one of our choices. Okay, so the closest we have is 2970 because look, they want us to give the answer with 3 significant digits. Actually, it should be 2, but since this is a 7, they didn't want to take it to 3. I mean to 2. So then my answer will be 2970 Kelvin. Okay. So now you should be able to use what we learned in this problem to do 18, 17, and 16. Remember, the rate at which energy is radiated from the star is a joule per second, which is, of course, a watt. The temperature has to be in Kelvin. So let me see. Everything is in Kelvin there. Now, right here, okay? Radiation, remember, the temperature needs to be in Kelvin. When we solve the problem, the temperature needs to be in Kelvin. Okay, with that, we will bring this chapter to an end. The ones that I worked out, class, the problems that I did together with you in the class, if you didn't get these answers, especially number 10 and number 19, work them again so that you can understand how the problem is solved. If you didn't get that answer, you need to work it again. Do we have any questions? Okay, if you don't have any questions, we'll close here. Remember, tomorrow, our class does not meet online, but I need for you to work on the final equation quiz. I have completed everything, I think, up to 111. So on Wednesday, we'll go through the gas laws. We'll talk about the wave equation, and we'll be done. And then we'll begin Thursday with our final exam review. Thursday, Monday, and Tuesday. Then Wednesday and Thursday of next week, we will have our final exam. So if I were you, I would start working on this now. You don't want to wait till the last minute to start reviewing. We've covered quite a bit of material. I sent this to you so that you can start now to go back to chapter 1 with our conversion equivalents, Pythagorean theorem, our basic understanding of motion, some of our derived units. I wrote them out for you here so you can have a better understanding of these units and words. We have our equations for understanding speed. Then we have the kinematic equations, two-dimensional motion, force, circular motion, working energy, power, momentum. This is angular motion equations, density, pressure, temperature conversions, heat exchange, all the way down to where we are now with heat transfer. So I will begin now to review so that come Thursday, you won't have as many questions. All right, 2:45, you can sign out now, and I will see you all on Wednesday. Oh, and this assignment that I just gave you here is due on Wednesday. So you have this assignment and the equation quiz that you want to complete before Wednesday. Have a good afternoon.